1, Section 3 of Chapter 5. Okay, let's go. So the first thing you're going to notice, if you're keeping track at home, keeping score, my title is different from your textbook's title. Alright, now if you let your mind float back to Chapter 4, we discussed the result that I called the dimension theorem, right, which was specifically the key ingredient in proving that two bases for a vector space have to have the same cardinality. Right, and the specific result that I referred to as the dimension theorem was that any linearly independent subset of a span can't have more things than were in the set that created the span. Right, so sort of formalizing what we had seen before, right, with, like, say, 3 vectors creating a span and those not being linearly independent, and then being able to find a smaller set that was linear independent that had the same span. Right. So I called that a dimension theorem, and then I noted that that's not really a universal name for that theorem, depending on what you're reading, what textbook, or what mathematician you're talking to. They'll just say, like, oh yeah, that's just true. They won't give it a fancy name. But I like calling it the dimension theorem. I've seen it called the dimension theorem in a couple of spots, so it's the name I went with. And then your textbook calls this section the dimension theorem. And I thought that was weird. And especially when I saw what they were calling the dimension theorem. And I've been ragging on your textbook. I've been banging on it. I've been saying it's not necessarily the best. The ordering of topics is a little weird. It's made some of the proofs more clunky than they needed to be. And now we get to this one. And they give this theorem the name the dimension theorem. That's the last straw. I am now on record. This book is awful. I didn't choose this book. I had no control over it. So I'm not to blame here, but man. So they call the Rank-Nullity Theorem the dimension theorem, and that is easily the single dumbest thing I have ever heard in my life. No human being on Earth calls the Rank-Nullity Theorem anything other than the Rank-Nullity Theorem. It was like aghast. Now I'm thinking, like, this is on purpose. They, like, purposely wrote a terrible linear algebra book or something. Like, it's like at the point now where you're like, this has to be, like, deliberate. There's no way you accidentally did this. You know, I don't know. I've almost spent 3 minutes ranting about this textbook, but anyway. So they call this section the dimension theorem, and what they're really talking about is the Rank-Nullity Theorem, which is a absolutely fundamental theorem of linear algebra, and they gave it their own stupid name. What a bunch of arrogant a-holes. Anyway, alright. So, today we're going to prove a fundamental theorem of linear algebra, the Rank-Nullity Theorem. And before we go into it, I do want to brace yourself for this. This is a lengthy one, 26 slides, as you can see. And the last 8 of them are a proof. That's not a difficult proof, but a proof that's just got a lot of steps. So we'll get into that a little bit later as we go here. But alright, let's recap where we're at and give some context to the absolutely fundamental Rank-Nullity Theorem. Okay, so a function is said to be linear if it respects scaling and addition. Okay, so hopefully we've got this drilled into our brain now and we're pretty comfortable with that definition. Recall that there are 2 subsets associated with a linear function that we're going to care about quite a bit. So the kernel, the set of inputs that all map to the same output, specifically the identity element in W, the 0 vector of W, and the range, the collection of all possible outputs. So recall that we proved that both of these sets have to be subspaces. Specifically, the kernel is a subset of the domain of V, and the range is a subspace of its codomain. And note, I'm making a distinction between range and codomain, and you should too. Right, the range is the collection of outputs. Codomains are any set that contains the range, so that we can always view f as a function between v and w, even if it doesn't hit everything in w. That's fine. Worth noting that some mathematicians don't do that. They make a distinction. They would say that a function to its range and a function to a codomain, even if they are the same function, are technically different, but I don't make that distinction. All right. So let's talk about these things in terms of a matrix, because given any matrix, we can create a linear mapping, right, by taking input from Rn and just multiplying the matrix. And as we proved, every linear mapping from Rn to Rm looks like this, right, and then similarly, every linear mapping between an n-dimensional vector space and an m-dimensional vector space can be represented as a matrix. The kernel for this linear mapping corresponds to the set of vectors out of Rn so that the output is 0. So, in other words, precisely the collection of solutions to the homogeneous matrix equation Ax equals 0. So the kernel now of this linear transformation is related to a set involving solutions to a matrix equation. And likewise, the range of this linear mapping is the set of vectors so that the matrix equation actually has a solution. Okay, nice. So we've actually previously seen that those are subspaces, but now we've got a different context for them. They are subspaces that precisely are a kernel and a range of a linear transform. So once again here, we're seeing that all of the stuff we were talking about with matrices really were specific instances of linear transformations. Right. So, let's push this a little bit further. The dimension of the range of that linear transformation, the dimension of the subspace of all vectors so that Ax equals b can be solved, so the b vector specifically. The dimension of that we're going to call the rank of the matrix. So, like I said, continuing to poo-poo our textbook, right, they've already talked about rank, and they talked about it way earlier, because they were basically talking about a dimension of something, but they didn't quite have the language for it. And now we do. All right, so the rank is the dimension of that subspace. Okay. So note that it's a subspace of Rn, so the dimension is no bigger than Rn. Right? It's potentially smaller than Rm, but there we go. Now remember, a subspace is just a vector space inside of it, right? It's closed under scaling and addition, so it's a vector space in its own right, so it has dimension. Okay, so here's the first time we're talking about subspace and dimension. And note that that is a subspace, so it's got to have that. Okay. We're now going to push this a little bit further. So, hey, rank of a matrix, part of the Rank-Nullity Theorem. So it turns out that the rank, actually, we can have a better bounds. Note that the rank is less than the number of rows of the matrix. It turns out you can always guarantee it's less than the number of columns as well. So specifically, let's say we've got a matrix, and then we isolate its columns. The column space is the span of its columns. Hence the name. Right? Just take the columns and span them. Note that it's a subspace of Rm again, because the columns are elements of Rm. There are m entries in them, because there's m rows in the matrix. So, here's what we're going to prove. The column space and the range are the same thing. Which means that the rank, another way of thinking about it, is the dimension of the column space, the collection of things that are linear combos of the columns. And because of that, there are n things here, so its dimension is no more than n by the dimension theorem, our thing that we're calling the dimension theorem, and thus we actually get a nice approximation for the rank. It's less than or equal to both the rows and the columns. Okay, and again, the rank being the dimension of the collection of all things that can have matrix equations that have solutions. All right. Okay, a little theoretical, right? A lot of new terminology and language, so let's do a proof so we get a feel for it. We are going to ground this in some specific matrices, but I want to hold off on that until we actually prove the Rank-Nullity Theorem. So bear with me for a moment. So let's do this proof. This is a classic unravel definitions proof. So take something out of the column space. That means it's a linear combo of the columns. And what do we know about linear combos involving the columns? That's the matrix equation. So anything in the column space gives us a matrix equation that can be solved. So it's got to be in the range of the matrix. Okay, so again, this set, remember, is the range of the linear transformation induced by the matrix A. Right. Specifically, it's equivalent to the set of things so that A times something equals it, so that it is something that ensures the matrix equation is solvable. Okay, so this was literally unravel definitions, and once again, here we see this rewriting the matrix multiplication as a linear combo of vectors, right? So a linear system of equations can be written as a matrix multiplication, which can be rewritten as a vector equation. That sort of trichotomy there is very powerful and right, the core of a lot of proofs of linear algebra. All right, well, it's an infinite, we're showing two sets are equal, so I just showed that the column space of A is a subset of the range induced by the matrix. So let's go the other way. So let's say you've got a element that is in the range of the linear transformation induced by the matrix. So that means it's equal to A times C for some vector C, and there you go. All right, just do the proof that we just did, but rewrite it backwards. And it works. Mutatis mutandis. And we're good. All right. So there we go. The column space, the span of the set of columns, is precisely the things that can give you matrix equations with solutions, which are precisely the things that are in the range of the linear transformation induced by the matrix. Right? So we've got multiple ways now of thinking of the exact same thing, and that is always a good thing. All right, so let's finish up the proof. So by part A now, well, the dimension of the column space is the dimension of the range of the linear transformation induced by the matrix, which we define to be the rank. So we now have two ways of thinking about the rank of a matrix. In most applications, thinking about it as the dimension of the column space is usually the better thing, easier thing. I don't know. Depends on the context. We'll see. All right, and then now, given any basis for the column space, that is a linearly independent set contained inside of a span. So by the real dimension theorem, the cardinality of B cannot exceed n. It's got to be at least n. It's probably less, right? If the columns of the matrix are not linearly independent, obviously, we can throw something out. So that means the dimension of the column space is no bigger than n. So the rank then can't be bigger than m or m, so it's at least the minimum of the two. All right, nice. So the rank of a matrix can never exceed the number of columns or the number of rows. Nice. Okay, and like I said, this is pretty abstract stuff we're talking about right now, but we're going to ground it in terms of linear systems in a moment, because now we've got enough stuff and we've got enough proofs here that we can actually discuss the Rank-Nullity Theorem, except for one thing. We need, well, what the hell is nullity? Okay, well, we gave a kind of fancy name for the column space, right, the range of the linear transformation induced by A, right? It's really the column space in disguise. So the null space of a matrix is then going to be this set, right? The other thing, the kernel of the linear transformation induced by the matrix, we're going to call this the null space. So it's also the set of things that are solutions to the homogeneous equation. Note it's a subspace of Rn. Already talked about that. Okay. Yep. Not too far. So we're going to establish a connection between the null space and the column space. Probably, I don't know, the Rank-Nullity Theorem. Let's prove their names of the section. All right, before we actually do that, we're going to take care of a couple of special cases first. This is just going to make the proof of the Rank-Nullity Theorem move a little bit smoother. So what we're going to prove is the following. If the dimension of the null space is 0, then the rank has to actually be n. So note, if we're thinking about the matrix, this tells me that if my rank is n, my columns actually have to be linearly independent. And, right. And likewise, if the dimension of the null space is n, then the rank of the matrix has to be 0. And in fact, we're actually going to prove something much stronger than that statement. We'll see that when we get into the nitty-gritty of the proof. All right, so note here we're kind of taking care of, like, extreme cases. And also this looks just, like, beautiful, right, as a statement. The dimensional null space is 0, then the rank is n, and the dimensional null space is n, then the rank is 0. That seems to be indicating that the dimension of the null space and the rank together probably have like a bound or something. Oh, I don't know. I guess we'll see it in a moment, but let's do this proof. This will give us a pretty good feel for what the null space is really all about. Okay, so if the dimension of the null space is 0, what does that mean? Dimension 0 means that the empty set is a basis, which means that you're the trivial vector space. Specifically, you are the singleton consisting of the 0 element of your vector space. This is an Rn, so its 0 element is the 0 vector with n entries, 0 sub n. All right, well, what does that mean? That means that the matrix equation, the homogeneous one, only has the trivial solution. Okay. So, equipped with this, we can verify that the columns first have to be distinct. So specifically, let's take the columns. Let's say 2 of them actually lined up, different index. Then I can create a vector in Rn, specifically where a sub j is 1, a sub k is -1, and all the other entries are 0. Now, if I look at the matrix equation, which again is the linear combination of the columns, well, as I just set them up, I zero out everything other than a and k. I have a sub j and a sub k. A sub j is being scaled by 1. A sub k is being scaled by -1. So I've got a sub j minus a sub k here, and that's 0. But as we just discussed, the only way that happens is if the vector is 0, but I created a non-zero vector, so we've got a nice little contradiction. Okay. Right, and note, I need the j and k to not be equal, otherwise I can't actually define that function. That function would not make sense. All right. Beautiful. So now we know the columns are distinct, so now we can go after linear independence. Because again, stressing, when we're doing linear independence, you need distinctness. Otherwise, you can have some wonky stuff happen. All right, so now we're going to verify the columns are linear independent, which would then mean that the column space has dimension n, so the rank is n. All right, so set up the same way. Scale them up, add them up, equal to 0. What does that mean? The matrix equation is 0. That means that vector C needs to be 0. So there you go, boom, we're linearly independent. Right, so the proofs so far that we've been doing here are all reliant on this interchange of the matrix equation and the vector equation associated with the columns of A. Nice dichotomous results. So, all right, cool. So we've now proven that if the dimension of the null space is 0, the rank of the matrix must be n. All right, let's keep pushing it. We have a b to prove. Let's say the null space has dimension n. Well, it's a subspace of Rn, so it means it is Rn. So that means that the matrix equation is always 0 for any possible input. Okay. So in other words, as we've already discussed, if that happens, then your matrix must be the 0 matrix, right? Choose X to be the standard basis vector that forces all of the columns to be 0. And hey, all the columns are 0. That means the span is just the 0 vector, right? Every single one of these is the 0 vector, so any linear combination of the 0 vector just gives us the 0 vector, and hey, the column space is the trivial vector space, so it's got rank 0. Nice, all right. So here we see there is definitely some sort of connection between the rank and the column space and the null space of the matrix. The sort of extreme possibilities line up with each other. All right, well, let's now prove it. Okay, so here it is. The single most important fact in linear algebra. Not the single most, but definitely one of the more essential theorems. The Rank-Nullity Theorem. The rank plus the dimension of the null space must be the number of columns. Okay. So I'll repeat that again. The rank of the matrix plus the dimension of its null space is the number of columns. So the dimension of the column space plus the dimension of the null space is the number of columns. Right, so the dimension of the null space is sometimes called the nullity, and sometimes it gets a fancy symbol, but that is not fully standard, even though the theorem is called the Rank-Nullity Theorem. Sometimes people are just like, dimension of the null space, whatever, doesn't need a fancy name. Rank needs a fancy name, though. For some reason, that has to have a fancy name. All right. So this might, at first glance, just look like whatever, maybe a neat-looking theorem. But I claim that you've used this theorem repeatedly when it comes to linear algebra, especially when you're doing row reduction and solving systems of equations. It may not seem it, but you have, and we're going to work out the details of that proof here, and then we're going to ground this in an actual matrix, and then we're going to make the connection of this stuff, and then you're going to go like, oh, that's why this is super important. All right. This is the thing. This is what we're going to prove. So how are we going to attack it? Well, the first thing we're going to note is that we've already proven part of the theorem. If the dimension of the null space is 0, then we've already verified the rank has to be n, so the theorem definitely holds. 0 plus n is n. And likewise, so first note that means that I can assume the dimension of the null space is strictly bigger than 0. And similarly, the dimension of the null space, if that's actually equal to n, then the rank has to be 0, so then the result holds. So we'll go ahead and assume that the dimension of the null space is strictly bigger than 0, but is also strictly smaller than n, right? Because anything, if for the extreme cases there, we already know if it's 0 and if it's n, we're done. Okay, so it's got a dimension, positive integer, but less than n. So we can find a basis that has p things in it, but p does not exceed n, and p is at least 1. Okay, so the null space then, right, can be spanned by p number of vectors, where p is between 1 and n, strictly less than n. Now, that is a subspace of Rn, but it doesn't get all Rn, because its dimension is only p. So that means I can extend it, right? It's the span of this set does not fill up all of Rn. So that means there are things outside of the span, which means we can add them to the basis and get a bigger basis, a bigger linearly independent set. So I can find vectors from p plus 1 to n to extend it to be a basis for Rn. So right, we've talked about that you can do this in any vector space, in fact. If you've got a span and you find something outside of the span, well, then it has to be linearly independent. In other words, I can take that element, add it to the set that did the spanning, and that makes it a bigger linearly independent set. So we've already seen and discussed this, and now we're just applying it in Rn. Okay, so what's the secret sauce here? How are we going to pull this off? So remember, the V1 to VP, those are a basis for the null space, which means that if I multiply those things by A, I get 0. So these new things I've got, when I multiply them by the matrix, they can't be 0, right? They cannot be in the null space. If they were, then they would be in the span of that set, which would contradict that the full set was linearly independent, because it could be written as a linear combination of things from the set, which we know is another way of thinking about linear independence. All right, so when I multiply those elements by A, I get non-zero stuff. I bet it's a basis for, I don't know, the column space there. All right. oh, hey, look, I claim that's distinct at a basis. And thus, that would mean the rank is n minus p, because that's how many things are in this set. But I know what p is, it's a dimension of null space. Add it over, boom, proof is done. Alright, so let's do it. Alright, well, so first off, I want to verify it's actually distinct, because I need to be sure that there is n minus p things in this list. Alright, so suppose that happens, well, then their difference has to be in the null space. But that's contradictory, right? Because if v minus j, v sub j minus v sub k is in the span, well, you can add v sub k over. That would mean v sub j can be a linear combination of things, not involving itself. That would violate the linear independence. So, can't happen. That means it's got to be distinct. All right, and then the linear independence is proven basically exactly the same way. Because if it was, if you take scalar multiples and rework the equation, that gives you this linear combo, has to be in the null space. All of those scalars must be zero. If any one of them is non-zero, then we can rearrange all the equations and get that one of those elements was in the span, but that can't happen because that violates the linear independence. Okay, I'm leaving some details out here. There, again, some technical gobbledygook involving, subscripts and, let's not get into that. But basically the same argument that I just did up here is going to apply. Just, you gotta manage the summations and the subscripts. So let's not worry too much about that. But basically the same proof works. Alright, so they're distinct and linearly independent. The only thing I need to verify now is that it actually spans the set. And equipped with that, then we've got a basis, and thus the Rank-Nullity Theorem falls. Okay. Alright, so pick something out of there. Then it's a solution to the matrix equation. Hey, I've got a basis for Rn. Those V1s, the VPs. And what did I say before? Well, when I multiply the V1 to VP by A, they're going to zero out. Ooh, which leaves over these things right here, which means B is a linear combo of those. So it spans, it's distinct, it's linearly independent. Bam, it is a basis, rank nullity, proven. Bang, bang, boom. And we're done, right? Not too bad. So that's kind of a slick proof. That's a neat idea. And when you kind of work through the details and see it, you go, you know what, yeah. So even at first glance, the Rank-Nullity Theorem just looks like, yeah, some stuff, sure, it's true. The proof really exposes, like, yeah, that's why it would totally be true. It's kind of a very natural thing to do, right? You look at your dimension of your null space. If it's trivial, then, well, yeah, the columns have to be linearly independent. If it's trivial the other way, if it fills up Rn, then yeah, the matrix has to be zero. There's no other choice. Right, so no, by the way, that incidentally proves that if you've got rank 0, then your matrix is 0. There's no other possibility. So rank 0 is usually, nobody cares about rank 0, because there's only one matrix that does it, but worth noting. Alright, and yeah, good stuff. And then if you're anywhere in between, then you can extend it to a basis, but if you multiply all those things by A, a whole chunk of them will evaporate because they're coming out of the null space. And then you're left over with this stuff, which would then have to span, then just verify that it's independent and distinct, and you got yourself a basis. Got yourself a basis going there. Alright. Nice. So, kind of a neat proof, and a real nice one. But like I said, sure, this is good and all, but there's a question. Alright. Now, I claim that the Rank-Nullity Theorem fully formalizes something you already know about how matrix works, how matrices work, specifically how linear systems work. So, let's take a matrix, my favorite one, sort of, 2x3 matrix. So, again, rank nullity is something that works for rectangular ones. It's really powerful for square ones. We'll get to that in a bit. Let's note that I can get a basis for this thing's null space by setting up the matrix equation AX equals 0, or in other words, looking at this linear system of equations. Now, I can turn that into an augmented matrix as follows, and then row reduce it, and get this. It's literally, scale this row, add it to that one, and then scale the second row to clean it up. I have, note, 2 pivot columns here, right? Pivot column right there, 1, 0, and a pivot column right there. Right, if I wanted to, I could, well, actually, yeah, that's not the reduced row echelon form now, is it? That should be a 0 up there. What's going on there? Oh, I didn't get, oh, yeah, no, I didn't do full out reduced. Yeah. Okay, yeah, alright, yeah. So you multiply it by -2 and add it up there. Let me fix that. That's not full out reduced. So okay, I didn't catch that. I put it in a computer and said, give me the reduced row echelon form. And I think I actually didn't say reduce, I just said, give me echelon form. So, anyway, I caught myself, right? I was like, wait, pivot columns, hold on, that's not, there we go, now it's pivot, blah, 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 there you go. That was dumb. Right, anyway. Okay, so anyway, if you want to formally work that out again. So you'd multiply the top row by -4 to make that 0. That would give you -3 right there, and would then give you -6 right there. Then you'd clean it up, and then you would get rid of the 2. Okay. So I was being lazy, and I made a computer do it, but I didn't actually say ref. I didn't say ref. I said just give me the ref. Caught it, though. Anyway, hey, 2 pivot columns. 1, 0, 0, 1 right there. Now, yeah, blah, blah, blah. So, yeah, now I gotta change this. This is totally, anyway, yeah, well, the second row still tells me that, but the first row, yeah, that quickly, tells me. Right, yeah, no, so then the second row tells me, bleh, that isn't right. That is completely a bugosity now. Yeah, I'm cleaning it up. Doing it live. I was doing good, man. I got that slide 17 before I was like, oh, wait, that's not right. Anyway, so, yeah, so the first one would tell me, of course, that y would be -2z, and the first one would tell me that, yeah, x has to be -z then. Right. Yeah. Because, yeah, you do the -2 there, -3, yep. Okay. So note, then, that means I have a free variable. I specifically have one free variable. So specifically, I can get a basis for the null space now. It's going to be, anything that's a linear combination of that beautiful vector right there. 2 pivot columns, 1 free variable. The dimension of the null space is 1. And by rank nullity, the rank then is 2. Ooh. So when you're dealing with linear systems and you're looking at your matrix, the pivot columns is the rank. The free variables is the nullity. Ah, there we go. So now we've got a wonderful connection. So that stuff we had done where you're doing the row reduction and you're keeping track of free variables and pivot columns, right? That's precisely what the Rank-Nullity Theorem is telling you. It's giving you a beautiful proof of something that we experience when we're doing row reductions. Nice. So it's worth noting the way your book handles the Rank-Nullity Theorem is to actually, and like I said, I skipped over it at first because I'm not a fan of doing it this way, where they're like, oh, the number of pivot columns is the rank. Right, that's true, but to me that's like just like a byproduct of the Rank-Nullity Theorem. It's not how you define it. But, no, that's how your book does it. But, anyway, beautiful, beautiful stuff. And, yep, you've probably been yelling at the screen going, that's wrong. And you're right. I felt it was wrong. In my bones, I was like, wait a minute, I don't think that's right. Yeah, it's not right. That's supposed to be -1. Right there. There we go. Now it's more cleaned up there. Okay. There we go. I knew this part was right, but then I was like, wait, I didn't do the ref right. Classic, like, you know, you make the one mistake, and then you're just immediately like, I don't know what I'm doing at all. Anyway, caught it though. That was a Bob Ross move right there. And you're like, wait, you ruined it. Or did I? Nah, I truly did. Anyway. Alright. So, as I promised, the back half of this is a proof that's 8 slides long. So it turns out that the Rank-Nullity Theorem can actually be proven for vector spaces in general, and in fact, there's actually a much stronger conclusion that you can make. Because the Rank-Nullity Theorem for vector spaces only needs the domain to be finite dimensional. The range can be infinite dimensional. Right, so what we're going to prove now is that if you have a finite dimensional vector space on a linear mapping, the range has to be finite dimensional itself, which shouldn't be too surprising. And then we get the Rank-Nullity Theorem. So, this is quite a nice fact right here. Okay, so now the proof of this is basically going to be the following. Well, we already proved it for matrices, so crowbar it into your vector spaces. Now, every linear mapping can be viewed as a matrix, as long as the domain and the codomain are finite dimensional. Now, the codomain is not necessarily finite dimensional, but I can change it to its range, which is finite dimensional, so I do have a matrix. And once we get the matrix, that matrix has the Rank-Nullity Theorem, and the proof's over. And by the proof's over, I mean there's a lot of hoops you gotta jump through. So, this proof is not hard, it's just got a lot of steps. So I was reading something where somebody was... So specifically, I was reading the companion notes for a book called Principles of Mathematical Analysis by Walter Rudin. And the companion notes had a difficulty rating for proofs from 1 to 5. And 5 was always reserved for a proof that was truly difficult. And they always wanted to go, difficult does not mean a number of steps. Right? A truly difficult proof could possibly only have one step, but the step was so obscenely out of... it required such a level of ingenuity that it's not trivial. So they were like, so a proof could be ranked as a 2, but it could be obscenely long. It's just that all the steps you have to do, you know, they're just, you do this, you do that, you do this. So in the bonus notes, I'm going to talk about a theorem that's pretty old. It's from 1932. And the standard proof is really easy. And that's standard. The original proof is a 2. It's got a lot of steps, but it's really obvious. But the current modern proofs are just like magic. They're like 5s. You do a bunch of stuff, and all of a sudden you're done. And you're like, why am I done? But anyway. So this proof here would rank a 2. None of the ideas are obscenely difficult. It's just a lot of stuff that you gotta do. So let's go through it. So the first thing to note is that if the dimension of the vector space V is 0, then it's the trivial vector space, which means that the range is trivial because it's a linear mapping, so it has to send the 0 vector of V to the 0 vector of W. So then, yeah, you just got a bunch of zeros adding up, so proof's done. Okay, so that means we can go ahead and assume, without loss of generality, that the dimension of V is non-trivial. Now we still am going to have to handle another trivial case, so let's now set up the basis for V. So the dimension is greater than 0, it's a positive integer. So we're going to claim that T of V has to live in that span, which then ensures that it's finite dimensional, because any linearly independent subset of the span can't have anything more than n things in it, by the dimension theorem. Alright, so pick something out of V. Well, then it's equal to some output of T at V, but V is a linear combo of V1 to Vn, so there you go. Bing, bang, boom, we're done. It's got to be in the span. Alright, now we're going to take care of another trivial case. What if the dimension of the range was trivial? Well, that means the range is trivial, which means, my function has to be the constant function, which means its kernel is all of V, which gives me the dimension theorem again. So that trivial case we can exclude. So we can assume that it's strictly positive. So we'll let that be M. Okay, so we're letting the dimension of the vector space be the domain of the linear transform. That is N. The dimension of the range of the linear transform, we're setting that to be M. That means there is an M by N matrix that represents the linear transformation, because it is a linear mapping between finite dimensional spaces. And boom, there we go, we've got our matrix. That is going to be the thing we're going to invoke the Rank-Nullity Theorem with. Okay. So note we proved last time that this is true. Alright, so here is the proof strat. We're going to demonstrate that the null space of the matrix is the same thing as the kernel. By that I mean they're going to have the same dimension. And likewise, the rank of that matrix is the dimension of the range of the linear transformation. And then by the matrix version of rank-nullity, the vector version of rank-nullity has been proven. Okay. So that's what we're going to have to prove. And like I said, this proof is very straightforward. It's a lot of steps, and it's pretty natural that this is what you would do, right? Convert your linear transform into a matrix. The matrix has the Rank-Nullity Theorem, so just pull it back. Alright, and here are the details for it. So let's go through, because again, none of what I'm about to do is particularly super deep in terms of mathematics. It's just, yep, this is obviously what you would do, so let's do it. Okay, so the first one that we want to hit up is if the dimension of the null space of the matrix is 0, that means the null space of the matrix is trivial. So if we take an element out of the kernel of the linear transformation, then that has to be trivial. So the null space, so the kernel of the linear transformation then is trivial, so the dimensions line up. Okay, so again, here we just took care of a trivial case, so we'll go and assume that the dimension of the null space of the matrix actually has something in it. So take a basis for it. Now note here where the dimension is P for the null space, so we don't know exactly what it is, but it's some number between 0 and n. Strictly positive. Now, there have to be elements of V whose coordinate vector line up with those. Right. Given any element out of P, it's in Rn, and so we can create a coordinate vector for it. So, quick math. These things are contained in the kernel, right? Because the way the matrix work, it represents the linear transformation in terms of coordinate vectors. They have to be distinct because, well, if they line up and the coordinate vectors line up, and that means those elements of Rn line up, but those are distinct to their basis, so there we go. And they have to be linearly independent because set up the linear combo, it's in the vector space, shove it through the coordinate vector transformation, that now gives you a linear combination in Rn, but these are linearly independent, so there we go. Alright, so basically what we're doing is we're taking a basis for the null space in A, and we're going to turn it into a basis for the kernel of the linear transformation. Because as we already established, the null space of a matrix is really the kernel of a linear transformation in disguise. Okay, that's exactly what we're doing. So that was what we started with, that's how we're ending things today. Alright, so now the only thing to verify is that if you're in the kernel, you're a linear combination of those things. Well, if you're in the kernel of the transformation, that means you are in the null space of the matrix, so you can be written as a linear combination. And as we discussed with coordinate transformations, that is a nice operation. And specifically, if two coordinate vectors line up, then the vectors themselves must be the same. And hey, there you go. That's got to be a basis for the kernel. Well, we know the dimension then have to line up. Nice. Alright, so the dimension of the null space of that matrix, which is representing the linear transformation, has got to be the dimension of its kernel. There we go. Alright, one last thing to prove. The dimension of the range of the linear transformation is the rank of the matrix, is the dimension of its column space, is the dimension of the linear transformation induced by the matrix, because this linear transformation K is being represented by this matrix. Alright, so take a basis for the range. Now, we already said that this has to equal M, so we don't have to do any trivial cases. Alright, so these are elements in the range TV, which is a m-dimensional subspace, so we can represent it as things in Rm. So give it the coordinate vectors, and again, quick math. These things have to be in the column space because, right, they line up with some output for your linear transform, but the linear transform is being represented as the matrix, so they have to be in the column space. Okay. Now, again, they have to be distinct by the exact same argument from before. These things are distinct, so when you shoot them into coordinate vectors, distinctness is preserved. And by the exact same argument we just did before, these are going to be linearly independent. You can work out the details if you really want. Again, like I said, the details here are not particularly enlightening or illuminating. They're just, yes, this is literally what you would do. Alright, and now let's wrap this whole party up. The last thing we need to do is actually verify that we've got a basis for the column space, and thus the rank and the dimension of the range of the linear transform are the same, completing the proof. Alright, well, if you're in the column space, then you're a solution to the matrix equation. So I can find a coordinate vector that lines up with that. That means that has to be in the range, so it's got to be a linear combo of that stuff. But the matrix represents the linear transformation T, and boom, we're done. It spans it, so it's a basis, and thus the rank of the matrix and the dimension of the linear transform will line up. And we're done. Yeah. Oh, we're going to finish at 45 minutes. Oh, wait, no, it says 46. No, damn it. Oh, well, bye. Like, comment, and subscribe.